Hello everyone, good afternoon. Today I'm here to present the work that I did last summer as part of the Data Science for Social Good Fellowship. So the topic for this talk is how do we evaluate machine learning algorithms which are designed to cater to the needs of school districts to identify students who are at risk of adverse academic outcomes. So before we begin, let me talk a little bit about the setting, what are the goals we are looking at, and a few basic things. So the goal of the school district is primarily to help as many students graduate high school on time. And the challenges to this goal are, pretty much there's lack of motivation, there's lack of skills, there are some health, economical, and various other issues that, can play a huge role in a student not succeeding in doing the same. So what is the solution? Of course, to provide appropriate interventions. But the bigger question is, how do we even identify such students who are in need of the interventions? So traditionally, schools have been using techniques like, look at their report cards and, teachers talk to the students or counselors discuss with students to determine the set of students who need interventions or who are at risk of some adverse academic outcome, right? But all these traditional methods, which involve human judgment, are of course expensive, time-consuming, and also error-prone. So since, of course, we are at KDT here, we would like to apply some data mining and see if we can improve this process any further. So just to give a brief overview of how a data mining framework for identifying students who are at risk of adverse academic outcomes would look like. So this is like the data about students where you have some attributes, age, gender, and so on. And you have also collected historical data about if a student has graduated on time or not, right? So this is the typical training data as we can think about it. So now that's the outcome variable, which is not graduated on time. So we throw all this data into a learning algorithm. Of course, when a test data point comes in, we want to predict if a student is likely to graduate on time or not. So that's the predicted outcome. So this is the overview of the system. Now, how are these kinds of frameworks evaluated? Of course, area under the curve, you have accuracy, you have precision, recall, and so on, right? So typically something like this. This is a ROC curve, and then we would measure the area under this curve to basically make sure that an algorithm is performing well. This is how we evaluate most of the learning algorithms. So are these metrics good enough? So are these metrics good enough to convince educators to use a particular algorithm as opposed to something else, is the question that we'll be trying to answer here. So turns out not, but I'll go into the details as to why and what can we do to help them convince in a better way that an algorithm works. So what is the setting that we are looking at? School districts typically have resources to help out students, but the problem is these resources, it's a little harder to determine the exact number beforehand, or these resources are also very dynamic in the sense that, for instance, in one of the counties that we worked with, the resource allocation increased by like 25% from 2000 to 2001 to help students. And also, resources can be added dynamically during a particular academic year itself. So resources are also limited and they're very dynamic, they vary a lot with time. Now, secondly, another important thing is we want to predict this risk as early as possible, right? So because, first of all, it's very hard to intervene once student either starts failing grades or he has already, kind of fallen behind during his course. Secondly, though we don't have an exact estimate, school districts would ideally like to get like a ballpark estimate of what is the amount of resources that they would like to, or that is required to be invested into helping out students. So given these requirements, now how can we think about evaluating the learning algorithms in this setting? So along with the main considerations that we just talked about, a couple of other things that school districts consider absolutely important are, when we give them an algorithm, we also need to give them some idea about what are the mistakes that the algorithm is making, or what are the kinds of data points on which the algorithm is likely to make mistakes. And lastly, but also more importantly, we also need to give them roughly an idea about what are the features an algorithm is using extensively. The reason behind this is whenever people are trying to deploy these algorithms, if the data on which these algorithms are operating has certain patterns on which the algorithms are making a lot of mistakes, or the features that the algorithms are using heavily are like erroneously encoded or they are missing, then it's a good idea to use something else and not the algorithm under consideration. So given all these, the setting that we talked about, so what is our goal? Our goal is to basically come up with an evaluation framework which basically is able to address all these aspects. So we are given as an input an algorithm for the student risk identification, and we need to be able to evaluate the reliability and goodness of the algorithm's risk scoring. So we'll talk a little bit more in detail what do I mean by that. And we also need to be able to evaluate if an algorithm is identifying risk in a timely manner. We should provide an interpretable characterization of the algorithm's mistakes. And we also need to provide to the educators a good understanding of what are the features that the algorithm is relying very heavily upon. So coming to the problem setting, so today, as I said, the input is already an algorithm. So we have decided that there are enough algorithms in literature for us to propose something new. So our focus is to kind of like think more about the evaluation metrics in this scenario. So in this talk, I'll look mostly at 3 algorithms: random forest, decision trees, and regression. We also looked at a few other commonly used machine learning algorithms, and the details are in the paper. So, and the problem setting, so this is the data that we have, a couple of counties, Montgomery and North Carolina public schools. So we have like, close to 25K students combined, and we have data available from all of these students, either from 6th to 12th grade or from 8th to 12th grade. And we have a bunch of attributes. So the last, the rightmost one, which is do not graduate on time, is our outcome variable. So one important point to be noted in this setting is that typically whenever people propose an algorithm, even for solving this problem of identifying at-risk students, they have always been traditionally using the train and the test set within the same cohort of students. Whereas in a more realistic setting, the way schools would use the data is that they use all the historical data for training, and they would, the next cohort or the upcoming cohort will be the one on which the testing happens. So just to kind of be true to that setting, we evaluated, we did all the work just like that, just in that setting. So the first metric, or the first scenario of evaluation that we'll talk about, is seeing how good are the risk scores provided by an algorithm. So what do I mean by risk scores, right? So most of these algorithms, like regressions or decision trees or random forests, provide probabilistic estimates of, what is the probability of a student not graduating on time. So why do we need these as opposed to the 0-1 labels? The reason being primarily that, as we talked about earlier, the resources are like very dynamic, and we never know if we can intervene 500 students or 1,000 students or maybe just 20 students. So that number is very dynamic. So if I just have like a stipulated number of 0-1 variables on 0-1 labels on the students, it is very hard for the educators to like really narrow down the number or increase that number. So we rely mostly on the probabilities for ranking the students, so that the cutoff or the thresholds can be decided by the schools, okay? And we call these probabilities as the risk scores in this talk. So of course, mostly logistic regression and decision trees already give probabilities, whereas random forests, you can compute the risk scores by averaging the probabilities from multiple trees. So 2 metrics that we think are good evaluation cases for this setting. So one that we call as empirical risk curves, and the rest is something which is used in a very standard way, which is precision and recall at top K, which is in the paper. So let me talk a little bit about what is an empirical risk curve, right? So we rank students based on the probabilities or the risk scores that we have been using as a term, and we divide them into the percentile bins. And then we plot the percentile bin on the x-axis versus the mean empirical risk, which is the probability of a student in that bin not graduating on time, on the y-axis, right? So the students in the high-risk bins, typically are the ones who receive interventions before the students in the low risk bins. And how do we decide if an algorithm is good? This curve that we are plotting should be monotonically non-decreasing. Okay? So just to show an example, so this is the Montgomery County, and I was just saying the x-axis is the percentile bins, on the y-axis is the empirical risk, which is also the probability of a student in that bin not graduating on time. So you have curves for 3 different algorithms. So the curves should be monotonic. That determines the goodness of the ranking of the algorithm. The one tiny thing that we could see is that decision trees exhibit non-monotonicity, which means if we trust them at the 60th to like I think 70th percentile, it would be a problem, because you will probably end up providing interventions to less risky students compared to the more riskier ones. So ideally, you should look for monotonicity in these curves, right? The rest of the algorithms are doing pretty well. So the second and the most important thing is we also need to identify these students as early as possible, and also we need to identify them, before they start failing grades, which we briefly touched upon. So what do I mean by identifying these students as early as possible? So when an algorithm is fed data, like for example, till the end of middle school, like till the end of 8th grade typically, if an algorithm is able to recognize the risk by then, as opposed to an algorithm which can only identify the risk by looking at all the data till the end of 11th or 12th grade, the first one will obviously be preferred because it's able to diagnose risk much earlier. So that is an important attribute of a good algorithm in this setting. And the second thing that we look for is identifying risk before off track, which is that, so we want to detect if a student is likely to not graduate on time before even he starts failing grades, right? Later on, it becomes much difficult to catch up. So what is the metric that we are using in these two cases? For the first one, we have plot the precision at 5%, so that will be the y-axis of the plot. And then on the x-axis, you will see the grade till which will give the training data to the algorithm. So what do we need to look for in this plot? The earlier an algorithm reaches a higher precision, the better. Okay? And of course, the earlier it also stabilizes, the better, both. Okay? So if we see that, of course, random forest being the topmost curve, it's doing a pretty good job. Next, logit, and then the last one being decision trees. So we are looking for higher precision and an algorithm that gets to a stable point much earlier with very little training data is the better algorithm, right? So now coming to the second part, which is identifying risk before off track. So here the metric that we are looking at is what the ratio of the number of students who are at risk, who are identified before they even failed grades, to the total number of students who failed to graduate on time. Okay? So now this is the plot again, where you have on the x-axis the top k, which is the top x or the top k number of the most riskiest students, and then the y-axis is what is the probability of these each of these bins, or for each of these k, what is the probability of detection before a student even starts failing grades. Okay, so of course higher values are better, and again we can see that random forests are doing a pretty good job. So coming to the qualitative analysis, or like a more softer like a take on this topic of evaluation metrics. So one interesting thing which we often ignore in many data mining papers or work is that we don't try to spend a lot of time on understanding what are the mistakes being made, why an algorithm is making mistakes, what are the data points where it's messing up, and so on. For educators, it's actually a very important thing to consider. So in order to do that, we kind of identified certain patterns, and for each of those patterns, we computed the probability that an algorithm is making a mistake. What do I mean by that? So for instance, random forest is making a lot of mistakes on the patterns where the grade 8 GPA is greater than 3, the absence rate is greater than 0.3, and tardiness score is something which indicates the punctuality aspects. And decision tree is making mistakes on like another pattern. Now, so what do I learn from this? So why am I even looking at these patterns? So for instance, let's consider the case where the cohort on which an algorithm is supposed to be applied has many female students who are disabled and they have a high GPA. So obviously an algorithm that's making a mistake on that pattern is clearly not the one that should be used in that setting. So it's very important for them to identify these kinds of patterns before they apply the algorithms and not just looking at their accuracies, right? And lastly, it's also important for the algorithms to, for us to be able to provide an understanding of what are the features that the algorithm uses the most. And again, why do we need that? So for instance, let's say if logistic regression uses absence rate in grade 8 and gender as the most important variables, if there is a new cohort on which we want to apply this algorithm and we know that the variable is not reliable and it's erroneously coded, we might as well just not apply this algorithm and consider something else. So with that, let me conclude the talk. So here in this work, we kind of did an exhaustive analysis to bridge the gap between traditional machine learning metrics and the evaluations which are actually meaningful to educators. And we looked at several aspects like reliable risk estimates, early predictions, interpretability, and of course our framework has been proven to be very useful in deploying the solutions for machine learning in Montgomery and North Carolina public schools. Thank you.
Thank you. Thanks, Hima. We have time for 1 to 2 questions. So I think gentleman in pink, that's first. Yes, and then you second.
It's very quick. So
can you wait for the mic? Yes.
Fascinating research, but have you considered adding a geospatial attribute so that you can identify like at-risk enclaves within school districts?
So you're saying that, look at specific patterns within school districts or look at specific mistakes within school. Is that what you mean?
With the attributes, like with the students, you had age, gender, grade point average, things of that nature, and looking at something that had a geospatial aspect toward the students so that you could see if they congregated into certain areas.
I see. Yeah, so that's something it would be interesting, but unfortunately we did not have that attributes in some of the data we looked at. Later on there was more, but yeah, that would be something very interesting to look at. But we did not do it in this particular work. Yeah, thanks.
Yeah, that's a second question.
I was going to ask a similar question about grouping the students in a certain way, but in terms of like a network of friends and to see how their motivation changes.
Sure. So again, that is, I think, not the data that we can easily obtain because from schools, to observe a network of friends in the real world is, it takes a lot of effort to collect that kind of data, but definitely a great idea.
Yeah. Okay.
I think we may have time for one more question. Okay, here. Yeah. Thanks.
Hi. When I worked at the University of Technology, we did something similar about 15 years ago. We used age and we used sex and we used the schools that they came from, but we also did their field of studies that was in there. We did their home postcodes that we had in there, and also we looked at the progression of cohort over a couple of years. So we actually saw if they changed cohorts within the progression and that. So I'm wondering if you're actually interested in doing any of the time progressions by actually the field of study or by even subject results as well, and put those variations in.
Yes, I mean, that would be, of course, interesting to look at, the specific fields of studies and, see if these results can extend and so on. So the only kind of like subject-specific attributes we had in some sense, we did not know the specific field of study. All we had were like a couple of MAP scores, which is like, math percentile scores and middle school tests and so on. So, but we really do not have that level of fine-grained data, but that would be very useful.
Thank you.
Thank you.
Okay, so let's thank Hima again. Thanks.